So when we talk about proteins, we talk about different levels of structure, right? And so we did kind of a cartoon sketch like this that shows our backbone coiled up, continuing more backbone, and then we have these green side chains in the space in between, and those are attracted and lead to tertiary structure. Or if you have a second polypeptide that's not connected up here, then side chains from those two polypeptides can be attracted, and that is what we call quaternary structure. So this is a very simple drawing. Later in your lecture notes, you maybe saw a picture that looked like this, which is a more detailed drawing where we have our same backbone, and then you can see these green circles are the side chains. So those are these same side chains that are in space, and there's different types of attractions between those side chains. Okay, so what we want to be able to do is draw those ourselves. So I have a worksheet here that's going to help us think about these side chains and draw some of them ourselves. So this is saying first label each amino acid side chain. Then we're going to determine the side chain attraction between them. Sorry about the focusing here. And then we're going to do the hard part, which is to draw that attraction. Okay, so essentially we're going to come up with our own drawing of something like this, where we have our backbone and then those side chains are attracted to each other. So let's take a look at aspartic acid and lysine. So we're going to go here and find asp, which is aspartic acid, polar acid, and then lysine, a little further down here, has that protonated amine, so that's polar basic. Okay, so this is polar acidic and polar basic. All right, so you can go through each of these different amino acid pairs and look for those polarities. Each cysteine is polar, leucine and veiling are nonpolar, and you continue down. Okay, now once I have those, I need to think about what kind of attraction can I have between a polar acidic and a polar basic amino acid. Okay, and so to do that, I'm actually going to skip ahead to a drawing. Okay, and so this drawing would be comparable to the one that we saw on the front page where we had a polypeptide and then we had these side chains coming out. So side chains, side chains, side chains, side chain, side chain, and these are all side chains here, right? Everything that we have here, these are all, we're going to focus in on the side chains. Okay, so I'm going to take aspartic acid and I'm going to come over here, okay, and look at aspartic acid, and I want you to remember that this NCC, this is the part of the amino acid that's in the backbone, so we don't see that in the side chain. What we do see in the side chain is this here, so a CH2 and a COO minus. So if I want to take my protein backbone and say, what if an aspartic acid was connected? Then I come back to my periodic table, or sorry, my amino acids, ignore the backbone and write CH2, COO minus. And it's okay if you bend that and angle that just a little bit different to fit in your space. So CH2, COO minus. And a couple things I want to remind you about. This COO minus is a feature of our polar acids. And we've been noticing in these big molecules that charges are very important to look at too. Okay, now lysine, I want to do the same thing. Okay, so here's the backbone atoms. I'm not going to write those, and then I have 4 CH2s and an NH3 plus. Okay, so I'm going to write CH2 4, so I'm going to kind of shrink it down a little bit, and then I'm going to write NH3 plus. Okay, and again, to the things that we've learned before, when we see these protonated amines, we know that that is a feature of our bases, and we're excited when we see a charge here because that's going to be important for intermolecular forces. All right, so I'm thinking about, these are the two side chains that are reaching across this space, right? Reaching across this protein backbone. And so I could, right, take those and circle them and say, hey, here's a couple of side chains, right? Now, what's the strongest attraction between them? We have 4 attractions to choose from, right? We have disulfide bonds, which we'll see in a minute. We have electrostatic attractions. We have polar attractions and we have non-polar attractions. And within polar, we had a few details, a few options there, okay? But from strongest to weakest, these are our side chain attractions. So when I see a positive and a negative charge, that's going to be electrostatic, okay? Static is a separation of charge. So we have opposite charges here. And so I could draw some intermolecular forces. That's an attraction, right? Between those two, between the two charges, all right? And I would say that this attraction is electrostatic. All right, let's take a look at the next one, okay? So cysteine and cysteine. So if I go and I look at my table of amino acids, here's the backbone, ignore that, and then I have CH2 and an SH, all right? So CH2 and an SH, and then another cysteine. So remember, this is the backbone, so at the backbone I want to start with CH2, and then I want to write an SH, and I'm going to kind of do that backwards actually, because the S should be near the carbon that it's bonded to, and the H should be away from the carbon because it's not bonded to it. I can also add lines in here if I want to. So I kind of took this and I reversed it, saying backbone, CH2SH, backbone, CH2SH. See how those are the same thing? So these are both polar, but they should jump out at you as, ooh, sulfurs are unique, okay? And so what happens here is these H's are actually lost. Oxidation is lost, so we actually oxidize them, and we end up with a covalent bond or a disulfide bond. This is sharing electrons across here. So it's not an attraction, it's actually a bond. And that's why we say that that's our strongest side chain attraction. All right, let's take a look at the next one. So leucine and veiling. So these might feel a little bit tricky to draw. Here's my leucine, okay, but you kind of have the hang of it now. Ignore the backbone and then read it to yourself. CH2, CH, CH3 branches, okay? So if I want to do that, CH2, add lines if you want, CH, and then CH3 branches, okay? And then similarly, veiling, here's the backbone, and from the backbone I read CH, CH3 branches, okay? So from the backbone, I read CH, and then CH3 branches, okay? So when I look at these non-polars, these are fairly easy. This is gonna be a non-polar attraction. All I have is dispersion forces between these two, and so these are gonna be dispersion forces that hold these together. Dispersion, and that falls under the category of non-polar attractions. And I didn't write down here, this was my disulfide bridge. All right, let's take a look at two more then, okay? And so again, I didn't add the green, but let's add the green. This is a side chain attracted to a side chain, just like we talked about up here. This is a side chain attracted to a side chain, okay? So if I look at the next one, ASN and serine, so that's gonna be asparagine, ASN, and then a serine down here, okay? So asparagine is polar, serine is polar. And so when I look at that polar, that's gonna be a polar type of attraction. And let's draw it out to see which one it is, because we actually have a couple of options there. So asparagine, if you look at your periodic, or your amino acid table, read what it says. So after the backbone, we see CH2, C double bond O, NH2, CH2, C double bond O, NH2. If you want to add lines, you can, or not, okay? So that's the asparagine, so I'm doing D here. And then serine, if I look at that, I have CH2 and then OH, okay? And just to help me out here, little trick, oops, CH2 and then OH, I'm gonna actually spread that H out just so I can see the difference between the O and the H here, okay? So as I look at this, I see that I don't have charges, I don't have that acid-base piece. I have something better than just non-polar. I don't have this covalent bond, so it's polar, and specifically within polar, this is gonna be hydrogen bonding, because I see N's and O's and H's, and so what I see here is that my NH can be attracted to my O over here. If you remember, in hydrogen bonding, these H's end up partially positive because the N is pulling electrons away from them, and the O ends up partially negative because it's pulling electrons away from that H there. And so a couple other words that we use to describe these, this H here in hydrogen bonding we called the donor, and then this O we called the acceptor, right? So I have hydrogen bonding here. All right, and again, that's just a way to look at my two side chains that are attracting each other. All right, the last one is one that was mentioned in your lecture videos, arginine and asparagine. So let's take a look at those. Here's arginine, CH2, 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 and then a whole bunch of nitrogens, NH, C double bond, NH2 plus, NH2. So let's try to sketch that one out, okay? So I'm just gonna read it from what I see here. CH2, and I had 3 of those. And then I have that's bonded to an NH. Oops, bonded to a carbon. So I'm reading through here. CH3s, NH, C double bonded, C single bonded. So double bonded to an NH2 plus, and then single bonded to an NH2. Okay, and again I'm working on G here. And then on the other side, I've got ASN, which is asparagine right next to it. So backbone, and then CH2, carbonyl, and H2. So CH2, carbonyl, and H2. And you could write H2N, or you could write NH2, either way, okay? So as I look at these, I see that they both have a lot going on, right, in terms of N's and O's. So I can see the charge here. When I see that charge, that's telling me that this is a polar basic amino acid, and it's got that charge. I'll throw some yellow on there. And then over here, this looks basic, but remember, amides are not basic. This is just straight up polar here, okay? So asparagine is just polar. So when I have a base or an acid, something that's got a charge on it, and something polar, then what I have is definitely a polar side chain attraction. I have an ion, which could be positive or negative, and I have a dipole. All right, so I've got an ion dipole, and so I want to make sure that this positive is attracted to something negative over here, maybe the O, maybe the N. Both of those have relatively a lot of electrons on them, and that's going to be my polar ion dipole attraction. All right, so if we can just zoom out and see what we've done here, and see my desk too, okay? We started with these cartoony type drawings saying, yeah, there's these side chain attractions or disulfide bonds that's holding the tertiary structure together, or the quaternary structure if you have 2 polypeptides. And when we zoom in a little bit more, we can talk about the specific polarities, and then we can redraw those side chains and show intermolecular forces, a super strong covalent bond, or other situations where you have those intermolecular forces. Okay, so I hope that helps you kind of take this small picture and look at it in a lot more detail. And so practice these, draw some yourself. You've got more down here you can practice drawing, some in your lecture notes you could practice drawing, and I hope that helps you out.